Hello, today's topic of discussion is second order ordinary differential equation. This chapter consists of 6 modules. In module 1, we start with a brief discussion of ordinary second order differential equation. This will be followed by the existence and uniqueness theorem of the second order ordinary differential equation. We then look into the general properties of the solution, the Wronskian, some theorems involving Wronskian, and some very good examples. A second order ordinary differential equation is a relation given in the following form: d2x dt square is equal to f t x x dash. Here t is the independent variable and x is the dependent variable. The following examples: t x double dash plus sin t into x dash plus e to the power t x equal to cos t, x double dash plus alpha x dash plus beta x equal to 0, and x double dash plus t x dash plus sin x equal to 0 are some examples of second order ordinary differential equation. Please note, x double dash is d2x dt square and x dash is dx dt. Second order differential equation are having several applications in the physical systems of the real world. The most useful Newton's law of motion is given in the form of second order differential equation, namely mx double dot equal to some function of t x and x dash, which predicts the motion of a particle of mass m on which a force F is acting. Let x t represents the position of the particle of mass m having velocity x dash, and F be the total force influencing the motion of the particle, and total force may depend on position, velocity, and sometimes on time also. Vibrations in mechanical systems, for example, spring mass systems, pendulum, motion of the planets, and electrical networks, are some important fields of application in which a second order ordinary differential equation plays a very important role. Solving a second order differential equation in terms of elementary function is a difficult job to perform, and in particular there is no general method available to solve a very simple looking differential equation of the form x double dash plus pt into x equal to 0, where pt is a given function of time. So, we are able to solve only a few special linear differential equation of the form d2x dt square plus pt into dx dt plus qx into x equal to rt, where p, q and r are functions of t alone and sometimes constants. In general, the linear equation 2 cannot be solved explicitly in terms of elementary functions. To find the solution, we may use the tool of infinite series. The existence and uniqueness theorem. Many special functions such as Legendre's polynomial, Bessel's polynomial, Hermite polynomial, Chebyshev's polynomial, and their properties are studied using the tools of infinite series solution. Since in general it is not possible to find an explicit solution of 2, so our first attempt is to find conditions for which it will be having a solution. And in this regard, we now study the existence and the uniqueness of the second order ordinary differential equation. So, the theorem says, let pt, qt and rt be continuous functions defined on an interval a b. Let t0 belongs to a b and x0 and x1 are any real numbers, then equation 2 has one and only one solution on the interval a b, satisfying x t0 equal to x0 and x dash t0 equal to x1. Geometrically, if the coefficient function p, q and the force function r are continuous functions on a b, then 2 has a unique solution passing through the point t 0 x 0 and has a prescribed scope x 1 at t 0. Depending on the isolated force function R t, we may classify equation 2 as homogeneous equation and non-homogeneous equation. If R t is identically 0, then equation 2 reduces to the homogeneous equation given by equation number 3 as d2x dt square plus pt into dx dt plus qt into x equal to 0. In all other cases where R t is not equal to 0, we call the equation as the non-homogeneous differential equation. So, remark 1, if the coefficient functions p, q are continuous function on a b, then the differential equation 3 satisfying x t 0 equal to 0 and x dash t 0 equal to 0 will have only the trivial solution. We begin our study with second order linear differential equation which is homogeneous. Theorem 0.1 is very useful theorem, as at this point it will not tell us how to find all solutions or a solution satisfying a given set of initial conditions. We now look into this definition. The function x t is said to be a solution of 3 if x double dash t exists and is a continuous function on a b, and L x t, which is defined as x double dash t plus p t into x dash t plus q t x t equal to 0, that is the image of x t under the operator L is the 0 function. Since the differential equation 3 is a linear homogeneous equation, we may use the above defined linear operator to rewrite the left hand side of the equation as L x t is equal to x double dash t plus p t into x dash t plus q t into x t equal to 0. Now, by the linearity property and 0.1, we may observe the following important property of the solution of equation 3. If x t is a solution of equation 3 and C belongs to R, then C x t is also a solution of the homogeneous differential equation 3. If x 1 t and x 2 t are any two solution of 3, so is x 1 t plus x 2 t. And lastly, the solution set S consists of x t such that L x t equal to 0, it is x t is a solution of 3 forms a vector space. From the above remarks, it is clear that if we have two solutions x 1 t and x 2 t of the homogeneous equation 3, then any function of the form x t which is equal to C 1 x 1 t plus C 2 x 2 t will also be a solution. In fact, we have infinitely many solutions generated by the two given solution of the equation. At this point, we may ask the following question, that whether every solution of 3 which is of the form 5, that is, does the solution represented by 5 is the general solution of 3 or not. The following theorem shows that the answer is yes. The theorem says that if x 1 t and x 2 t be any two solutions of 3 on the interval a b, such that the expression x 1 t x 2 dash t minus x 1 dash t x 2 t is not equal to 0 for all t belonging to the interval a b, then x t equal to C 1 x 1 t plus C 2 x 2 t is the general solution of the equation 3. The proof goes like this. To show that x t is the general solution, we first have to show that any solution y t of the differential equation 3 satisfying some initial conditions at a time t 0 belongs to the closed interval a b, say y t 0 equal to x 0 and y dash t 0 equal to x 0, can be represented as y t equal to c 1 x 1 t plus c 2 x 2 t with some suitable constants c 1 and c 2. Now, if such constants c 1 and c 2 exists, then they must satisfy the following two conditions: c 1 x 1 t 0 plus c 2 x 2 t 0 equal to x 0 and c 1 x 1 dash t 0 plus c 2 x 2 dash t 0 equal to x dash 0. We rewrite this system in the matrix form as given in equation number 7. The linear system 7 will have a unique solution c 1 and c 2 if the determinant x 1 t 0, x 2 t 0, x 1 dash t 0, x 2 dash t 0 is not equal to 0. If we expand the determinant, we will be getting x 1 t 0, x 2 dash t 0 minus x 1 dash t 0, x 2 t 0, which is not equal to 0, which follows from the given assumption of the theorem that x 1 t x 2 dash t minus x 1 dash t x 2 t is not equal to 0 for all t belonging to the closed interval a b. By applying Cramer's rule, we get the solution of c 1 c 2 to be c 1 equal to determinant x 0 x 2 t 0 x 0 dash x 2 dash t 0 divided by x 1 t 0 x 2 t 0 x 1 dash t 0 x 2 dash t 0, and c 2 is also given by x 1 t 0 x 0 x 1 dash t 0 x 0 dash divided by determinant x 1 t 0 x 2 t 0 x 1 dash t 0 x 2 dash t 0 given by equation number 8. We now define x t equal to c 1 x 1 t plus c 2 x 2 t, where t belonging to the closed interval a b, where c 1 and c 2 are constants given by equation 8. The function x t is a solution of the differential equation 3, as it is a linear combination of two solutions x 1 and x 2. Also, x t 0 equal to x 0 and x dash t 0 equal to x dash 0 by the choice of c 1 and c 2. Thus, y t and x t both satisfying the same differential equation 3 and the same initial condition, and therefore, by theorem 0.1, y t is equivalent to x t for all t belonging to the closed interval a b, and hence x t equal to c 1 x 1 plus c 2 x 2 t, where c 1 and c 2 are constants defined as in equation 8. Theorem 0.2 is a very powerful result for studying the second order linear differential equation, as this enables us to write every solution, which are infinitely many, in a simple form with the help of any two solution x 1 t and x 2 t, satisfying the only condition, that is x 1 t x 2 dash t minus x 1 t x 2 t is not equal to 0 for all t belonging to the closed interval a b. And hence we define that let x 1 t and x 2 t be two solutions of 3 such that x 1 t x 2 dash t minus x 1 dash t x 2 t not equal to 0 for all t belonging to the closed interval a b, then x t is equal to c 1 x 1 t plus c 2 x 2 t, where t belongs to the closed interval a b, is called the general solution of 3, and x 1 t and x 2 t are called the fundamental set of solutions of 3. The quantity x 1 t x 2 dash t minus x1 dash t x2 t is known as the Wronskian of x1 t and x2 t and is denoted by w x1 x2 t is equal to x1 t x2 dash t minus x1 dash t x2 t. After defining Wronskian, we will now look into few properties involving Wronskian which will tell about the linear independence and linear dependence of the solutions of the second order ordinary differential equations. After that, we will take up some good examples. We now look into the following remarks. It can be proved easily that a fundamental set of solutions x1 t and x2 t are basically a set of linearly independent solutions. If C1 x1 t plus C2 x2 dash t equal to 0, then C1 x1 dash t plus C2 x2 dash t is also equal to 0. By Cramer's rule and the fact that x1 and x2 are a fundamental set of solution, it follows from 8 that C1 and C2 are both equal to 0. The dimension of the solution space for a homogeneous linear ordinary differential equation 3 is 2, and we are able to find a basis consisting of a fundamental set of solutions which are a linearly independent spanning set for the solution space. The condition that the two solutions x1 and x2 are fundamental is to check that the Wronskian w x1 x2 t is not equal to 0 for all t belonging to the closed interval a b. We now look into the following theorem. The theorem says let pt and qt be continuous functions on a b, then the Wronskian w of any two solution x1 and x2 of 3 is either 0 or never 0 on the interval a b. The proof is as follows. Since w x1 x2 t is defined as x1 t x2 dash t minus x1 dash x2, we differentiate the Wronskian to get w dash is equal to x1 x2 double dash plus x1 dash x2 dash minus x1 double dash x2 minus x1 dash x2 dash. These two terms cancels and we get x1 x2 double dash minus x1 double dash x2. Since x1 and x2 are solutions of the differential equation 3, we will be having d2x1 dt square plus pt dx1 dt plus qt x1 equal to 0 and d2x2 dt square plus pt dx2 dt plus qt into x2 equal to 0. Multiplying the first equation by x2 and the second equation by x1 and subtracting the first equation from the second, we will obtain x1 x2 double dash minus x1 double dash x2 plus p times x1 x2 dash minus x1 dash x2 is equal to 0, which may be defined as dw dx plus pw equal to 0, as w is equal to x1 x2 dash minus x1 dash x2, which is a first order linear differential equation whose general solution is given by w x1 x2 t is equal to w x1 x2 at the point t0 e to the power integration t0 to t ps ds, where t0 is any given time in the closed interval a b. Now, the exponential function always gives a positive value. So, the Wronskian of x1 and x2 is 0 for all t if and only if it is 0 at any point t0. Lemma 1. If x1 and x2 are two solutions of the homogeneous equation x double dash plus pt into x dash plus qt into x equal to 0 on the closed interval a b, then they are linearly dependent on this interval if and only if their Wronskian w x1 x2 is equal to x1 x2 dash minus x2 x1 dash is identically 0. Assume that x1t and x2t are linear dependent, and we show that x1 x2 dash minus x2 x1 dash is equal to 0. So, if either function is identically 0 on AB, then we have the clear conclusion. Then we assume that neither is identically 0, and it follows from this and the linear dependence that each is a constant multiple of the other, and accordingly we will have x2 equal to c x1 for some constant c, which implies x2 dash is equal to c x1 dash, and we can write x1 x2 dash minus x2 x1 dash is equal to x1, we replace x2 dash by c x1 dash minus c x1 x1 dash, which is equal to 0, and this proves the first half of the lemma. Now, we assume that the Wronskian is 0 at a point t0, that is w x1 x2 t0 equal to 0, and we want to prove the linear dependence. Consider the linear equations given by equation number 10 and 11, which is c x1 t0 plus c2 x2 t0 equal to 0, and c1 x1 dash t0 plus c2 x2 dash t0 equal to 0. Since w x1 x2 t0 is equal to 0, we have a non-trivial solution for c1 and c2. Let phi t equal to c1 x1 t plus c2 x2 t for a set of such non-trivial solution of 10. Since phi t is a solution of 9 such that phi t0 equal to 0 and phi dash t0 equal to 0, we have phi t is equal to 0 by theorem 0.1, that is c1 x1 t plus c2 x2 t equal to 0 for some non-zero c1 c2, and hence the proof is completed. We now look into few examples. The first one, we have to show that e to the power x sin x and e to the power cos x are the linearly independent solution of the differential equation y double dash minus 2y dash plus 2y equal to 0. And then we have to find its general solution and a particular solution. The equation is given by equation number 12. We assume let y1 x equal to e to the power x sin x and y2 x equal to e to the power x cos x. To show that e to the power x sin x is a solution, we just put this y1 x in this differential equation in the left hand side to see whether it is coming to 0 or not. Therefore, y1 dash is given by e to the power x sin x plus cos x, equation number 14, and y1 double dash is equal to 2 e to the power x cos x given by 15. We substitute all these values in the given differential equation and we obtain y1 double dash minus 2 y1 dash plus 2 y1 is equal to 0, which shows that y1 x is equal to e to the power x sin x is a solution of 12. In the similar fashion, we can show y2 x is equal to e to the power x cos x is also a solution of the given differential equation. Now, the Wronskian of y1 and y2 is given by wx is equal to determinant y1 x, y2 x, y1 dash x, y2 dash x. If we substitute the values of y1 and y2 by the actual values and we expand the determinant, we will obtain wx is equal to e to the power minus 2x, which is not equal to 0, showing that the Wronskian of y1 and y2 is not equal to 0, and hence we conclude that y1 x and y2 x are linearly independent solution of the given differential equation 12. The general solution of 12 is given by y x equal to c 1 y 1 x plus c 2 y 2 x is equal to e to the power x c 1 sin x plus c 2 cos x, where c 1 and c 2 are arbitrary constants. The given conditions are y 0 equal to 2 and y dash 0 equal to minus 3. So, we put x equal to 0 in 16 and we obtain the constant value c 2 equal to 2, and we put x equal to 0 in 17 and we obtain the constant value c 1 is equal to minus 5. Hence, the solution of the given differential equation satisfying the initial conditions y 0 equal to 2 and y dash 0 equal to minus 3 is given by y equal to e to the power x multiplied by 2 cos x minus 5 sin x. Our next example, we have to show y 1 x equal to sin x and y 2 x equal to sin x minus cos x are linearly independent solutions of the differential equation y double dash plus y equal to 0. And in the second half of the problem, we have to show that we have to determine the constants c 1 and c 2 such that the solution sin x plus 3 cos x is equal to c 1 y 1 x plus c 2 y 2 x. The given equation is equation number 18, also given y 1 x is sin x and y 2 x is sin x minus cos x. We find the value of y double dash x and y x and substitute in the differential equation to obtain y 1 dash plus y 1 is equal to minus sin x plus sin x equal to 0, showing that y 1 equal to sin x is a solution of the given differential equation 18. In a similar manner, we can prove that y 2 equal to sin x minus cos x is also a solution of the differential equation 18. To show that the solution y 1 and y 2 are linearly independent, we calculate the Wronskian, which is given by w x is equal to sin x minus cos x, cos x plus sin x. If we expand this determinant, we will get the value to be 1, and obviously it is not equal to 0, showing that y 1 x equal to sin x and y 2 x equal to sin x minus cos x are linearly dependent solution of the given differential equation 18. Now, in the second half of the problem, we have to determine the constants c 1 and c 2 such that sin x plus 3 cos x is equal to c 1 y 1 x plus c 2 y 2 x. We substitute the values of y 1 and y 2 in this equation to get sin x plus 3 cos x is equal to c 1 sin x plus c 2 sin x minus cos x. Comparing the coefficients of sin x and cos x from both sides of equation number 21, we will get c 1 plus c 2 equal to 1 and c 2 equal to minus 3, which will imply c 1 equal to 4. Our next example, we have to show that the Wronskian of the functions y 1 equal to x square and y 2 equal to x square log x is non-zero. That is, y 1 x and y 2 x are linearly independent. As before, we calculate the Wronskian of the functions x square and x square log x given by w x equal to determinant x square log x 2x log x plus x, and if we expand, we get the value to be x cube, which is not identically equal to 0 on minus infinity to plus infinity except plot x not x equal to 0. Hence, the solutions y 1 and y 2 can be linearly independent solution of the given differential equation. Now, in the second part of the problem, the general solution is given by y equal to a y 1 plus b y 2, which is equal to a x square plus b x square log x, where a and b are arbitrary constants. We differentiate equation 22 twice to obtain equation 23 and 24. We solve for a and b from 23 and 24. We next multiply both sides of 24 by x, and we get equation number 25, given by x y dash is equal to 2 a x plus b times 3 x plus 2 x log x. Subtracting 23 from 25, we get b equal to x y double dash minus y dash divided by 2 x, and substituting this value of b in 24, we will get a equal to 1 by 4 x multiplied by 2 x y double dash minus x y double dash minus y dash 3 plus 2 log x. Substituting both the values of a and b in 22 and simplifying, we get the required ordinary differential equation of second order as x square y double dash minus 3 x y dash plus 4 y is equal to 0. In the last example, we have to show that the three functions e to the power x, e to the power minus x and e to the power 2 x are linearly independent solutions of the given differential equation d3y dx cube minus 2 d2y dx square minus dy dx plus 2y equal to 0. The given equation is named equation number 26. We assume y1 x is equal to e to the power x, y2 x equal to e to the power minus x and y3 x equal to e to the power 2 x. We substitute y1 equal to e to the power x in the given differential equation, and we find that the right hand side is 0, which states that e to the power x is the solution of the given differential equation. And likewise, we can check e to the power minus x and e to the power 2 x are also will be the solution of the given differential equation. We next calculate the Wronskian of y1, y2 and y3, which is given by w x is equal to determinant e to the power x, e to the power minus x, e to the power 2 x, e to the power x minus e to the power minus x 2 times e to the power 2 x, e to the power x, e to the power minus x 4 times e to the power 2 x. And if we expand this determinant, we will be getting the value to be minus 6 e to the power 2 x, which is not identically 0 on minus infinity to plus infinity, and hence we conclude that y1, y2, y3 are linearly independent solution of the given differential equation. And since the order of the given differential equation is 3, it follows that the general solution of 26 will contain 3 arbitrary constants, and hence the general solution of the given differential equation will be y equal to c1 e to the power x plus c2 e to the power minus x plus c3 e to the power 2 x. In module 1, we look into the general solution and the properties of the second order ordinary differential equation. In module 2, we will look into another important method, namely the variation of parameters of solving the second order ordinary differential equations.